Okay, so we ran out of time with that last video, but just wanted very quickly to recap. What had happened was we had rewritten our differential equation by separating the variables, and this is what we see in yellow right here. But on this left-hand side, we noticed we had a partial fraction. So just as we had done yesterday, we did a partial fraction decomposition. We took that unified fraction and wrote it as a sum of two individual fractions multiplied by the least common denominator, chose some clever forms of p to substitute in so we could find a and b. Once we knew a and b were both 1 over 1,000, rather than write complex fractions, having a fraction within a fraction, I just pulled a out in front and b out in front as coefficients of those fractions. And what we now have very quickly in this highlighted portion is actually our differential equation separated, but in this much nicer form right now. And what we're going to do at this point, continuing, is we will integrate both sides. And as we integrate, you're going to see that the left-hand side is going to, and by the way, because population is positive here, we're going to be able to do something a little nicer. We're going to know that we'll have 1 over 1,000. We can write this as the natural log of just p. The natural log of just p here. Now, sometimes it's tempting to want to write this as absolute value of p, but we're dealing with a population of animals here, so rest assured we won't have negative amounts of those animals. As we take a look at the second integral, it's very tempting to think that we would just have 1 over 1,000 in natural log of 1,000 minus p. Again, the 1,000 minus p, we're guaranteed that this expression is positive as well. Remember that our carrying capacity is 1,000. And it's tempting to think that this is our antiderivative, but let's very quickly take a derivative to check. And you'll notice with the chain rule, a -1 would come out. So we'd have to compensate by dividing by that negative, which would change the sign. On the right side, we would see that we'd get 0.0003t. And just as we've been doing all along, we could say plus a constant. Now, at this point, if I may, I'd like to make a suggestion to multiply both sides by 1,000. Now, if we multiply both sides by 1,000, some nice things are going to happen. We will just have the natural log of p minus the natural log of 1,000 minus p. And from here on the right hand side, you can see we'll move our decimal 3 places to the right. We'd have 0.3t. Now, of course, technically you could say we'll have 1,000 times a constant, but what we could do actually is just say, look, it's just a different constant. Let's just keep it in this form. So tell you what, I'm going to bring this up to the top here. We're going to recopy this problem and continue working. So we've got natural log of p minus natural log of 1,000 minus p. So we can continue up here. We said that was equal to 0.3t plus a constant. And tell you what we could do even right now. This is kind of clever. We could use a property of logarithms if you'd like. This would be really nice. This would become the natural log of p all over 1000 minus p. So when you have a subtraction of logs with a common base, you may write them as the logarithm of the quotient of those arguments. So, tell you what, at this point, let's go ahead and find out what C is. Notice that what we have is that P of 0 equals 61. Now, what that's really telling us is this. T, remember P is a function of T, and that's what we're even getting very close to seeing right now. We don't have P alone. But what that means is that T equals 0 with P equals 61. So very quickly we could substitute in 61 for P and simultaneously allow T to equal 0. So I'm going to do a little bit of scratch work right here. And don't forget we still have our constant. So very quickly we could see that C then is going, well, and forgive me, I wrote 1000 minus P when I should have written 1000 minus 61. So the right side, of course, is just going to be a C. 1000 minus 61, well, that will just take you a moment, hopefully, to confirm to be 939. So this becomes natural log of 61 over 939. That's your C. So what does that mean? Coming back to this equation, rewriting it, we could say natural log of P over 1000 minus P equals 0.3T plus natural log of 61 all over 939. Now, of course, what they're asking us to do is to solve this differential equation. Do you know what we're really asked to do is to get P alone to find what P equals. So let's very quickly do a little bit of some cleaning up. I don't want to have P trapped inside of a natural log, so I'm going to raise both sides to the e to the left power, e to the right power, exponentiate, in other words. So what we'll see is P over 1000 minus P, and here we'd get e to the 0.3T plus natural log of 61 all over 939. And that is all a power of e. Now, just to clean this up even a little bit more, what we'll do is write this as e to the 0.3t times e to the natural log of 61 all over 939. But as we're looking more closely at that last term, we're going to be able to say now, look at that, that just becomes 61 over 939. And I'm going to bring that out in front. Okay, so we're getting closer and closer to getting P alone. And there are a couple of ways we could do that. If I may, though, I'd like to make a little suggestion on taking a reciprocal. We're going to take a reciprocal on both sides. So this is going to be 1000 minus P all over P. And here, if we take a reciprocal, we would actually get 939 all over 61. But don't forget, you'd actually have to take a reciprocal over here. But if I may, I'm going to write this a little bit differently. Yes, it would be 1 over e to the 0.3t. But for reasons you'll see in just a little bit, I'm just going to write it like so. So obviously we can always do this. We're saying, in other words, if A equals B, Then 1 over a, of course, should equal 1 over b. As long as you wouldn't have a and b equaling 0, this would always be true. That's all we're doing here. We're just taking the reciprocal of both sides, but instead of writing 1 over e to the 0.3t, we'll use that negative exponent idea. Well, why are we doing that? Well, we're getting closer. Tell you what, let's take our common fraction on the left and separate that. As we say in class, I heart math. So we'll say 1,000 over p minus p over p. We're getting close to being done. Let's see, we'll have this as e to the negative 0.3t. And of course, p over p is just a 1. So we're getting very, very close now to getting where we'd like to. Tell you what, I'm going to add a 1 to both sides. So just continuing over here, we'll say 1,000 over p equals 1 plus 939 all over 61 e to the negative 0.3t. Well, you might notice that we don't quite have p alone, do we? Let's take a reciprocal again. So we get p over 1,000. This time, I'm just going to write 1 over 1 plus 939 over 61 e to the negative 0.3t. And finally, one more step. Sorry for the dancing around here, but we've got p equals, multiply both sides by 1,000. 1,000 just comes up on top. Down below, we'd have 1 plus 939 all over 61 e to the negative 0.3t. This is your answer. This is your solution. You have your population now written with respect to time. But what I really want to point out is we were coming down to this very bottom. Take a look at what we have right here. That solution to the differential equation is always going to have an answer that can be written in this form. P is equal to m, and m was 1,000. We saw that in the very beginning of the problem. That's what we're seeing right here. We've got 1,000 in that numerator, so you can see that right here, divided by 1 plus some a, some constant. In this regard, that's 939 over 61. And that's e to the negative mk. K is actually the constant in the original part of the differential equation, times t. So a lot of work, but good practice, real good practice, on how to separate a differential equation, use partial fractions, and then just go through a lot of algebra on how to solve for p. So great, great practice. The homework that we're going to have is actually going to be a worksheet. So great practice on logistic growth differential equations. Good luck. Hope things are working out well.